So this is the correlated Rayleigh two random variables R1 and R2 which are correlated. And actually we know since R1 is square root of x squared plus y squared, x and y are identical, zero mean, equal variance, and they are independent. R1, R2 are separately Rayleigh. So this is their, so that means if you work out for R1, will turn out to be R1 over sigma squared e raised to minus R1 squared over 2 sigma squared. And R2 same thing. So on the other hand, I naught of A, as I said before, is 1 over 2 pi integral 0 to 2 pi e raised to A cos theta d theta. This, if you expand simply as a summation and do the integration on the cosine, this is easy to show. This will turn out to be k equal to 0 through infinity a to the power 2n over 2 to the power 2n over n factorial on n. This is actually n factorial squared. This is a standard expression. The way you do this is you expand this, and so notice that there will be terms of the form cos to the power theta to the power n, and that is a standard integral over n factorial. So when you substitute that, you will get this term. And notice that this is an even function of only even powers are retained. So if I substitute this for here, so let me substitute this expression. So this will now read R1 R2 over sigma 4 1 minus k squared e raised to minus R1 squared plus R2 squared over 2 sigma squared 1 minus k squared. And I'm going to substitute for the I naught function. So this is n equal to 0 through infinity a to the power 2n. So this is R1 to the power 2n, R2 to the power 2n, k to the power 2n over sigma squared 1 minus k squared to the power 2n and 1 over n factorial squared, I guess. And we have a 2 to the power, so 2 to the power 2n in the denominator. So we can use this expression to find out so if you want to write it a little more reasonable, notice that let me, rather than write it one more line, let me rewrite it in this manner. So that's going to be R1 squared over 2 sigma squared 1 minus k squared because we had 2 to the power 2 and all the terms we'll see are here. R2 squared 2 sigma squared 1 minus k squared all right, so we had R1 to the power 2n, which is here, and 2 to the power 2n I have absorbed here, 2 to the power n here, 2 to the power n here, and all the other terms are there. Okay. So all right, so what we need now is use this expression and find out, this is what we want to find out. We want to find out expected value of R1, R2. Remember, R1 is R evaluated at t, R2 is or the magnitude evaluated at t plus tau. So we are trying to find out the correlation between these two random variables. This is the joint density function. So if we can do this, this is simply R1, R2, FR, R1, R2, dr1, dr2, 0 to infinity, 0 to infinity. So for this density function, we substitute this here. So then this is going to read, so I'm going to pull out the summation outside. Summation n equal to 0 through infinity. And so this R1, R2 multiplied by R1, R2. So this reads now, I'm going to write down the results of what I have here. R1 squared, R2 squared, sigma 4, 1 minus k squared. So e to the power this term next. So that's R1 squared plus R2 squared over 2 sigma squared multiplied by 1 minus k squared. Then you have these terms. So R1 squared to the power 2 sigma squared 1 minus k squared to the power n, R2 squared over 2 sigma squared 1 minus k squared to the power n, then k to the power 2n. Remember, k is a function of tau over n factorial squared. So what is missing here is the integration. So integration is on R1 and R2, two integrals from 0 to infinity. dr1, dr2. So let me tell you the substitution to be done. So obviously you just substitute, this is obvious, one variable u, another variable v. And here onwards, and if you, so of course, then you notice that this will become u to the power n, this will become v to the power n. But du is going to be R1 dr1. So you have one R1 here, R1 dr1 is there, but one R2 will be remaining there. So if you look at all this, the expected value of R1, R2 will turn out to be, so the next step will be n equal to 0 through infinity, double integral 0 through infinity, 2 sigma squared 1 minus k squared over sigma 4 1 minus k squared, u to the power half, v to the power half. This is coming from here because we pick up R1, R2 will remain here. One R1 dr1 will give you du. So still there will be, so this is e raised to u plus v. That's this term. Because u is R1 squared over 2 sigma squared multiplied by 1 plus k squared. So that's simply u plus v. And then you have un, vn, du, dv. Then you have k squared tau over n factorial squared. And here, of course, you have sigma squared multiplied by 1 minus k squared. Same thing here, sigma squared multiplied by 1 minus k squared, because look at here. R1 dr1 is going to be 2 cancels, sigma squared multiplied by 1 minus k squared du, etc. So this, if you simplify, I'll write down the next simplified line. So this is 2 sigma squared 1 minus k squared, the whole squared, summation n equal to 0 through infinity, k to the power 2n over n factorial squared. Now the integrals become separate, u to the power n plus half e raised to minus u du. This is v to the power n plus half e raised to minus v dv. But each of those integrals are gamma functions. So this of course will be, you can just work it out. This will turn out to be n plus half and then n minus half etc. up to 3 by 2 multiplied by gamma half, which is square root of pi over 2. And consequently, we are almost there. This quantity will now be two sigma squared 1 minus k squared the whole squared multiplied by summation n equal to 0 through infinity. This term repeats twice. This also the answer is the same. So this will be 3 by 2, then 5 by 2, etc. up to n minus half multiplied by n plus half. This thing squared. Then you have the n factorial 2 times. Then you have k to the power 2n. Then you have pi by 4. But this whole thing, so pi by 4 multiplies as pi by 2 sigma squared 1 minus k squared the whole squared. And this is the definition of hypergeometric function evaluated at 3 by 2 comma 3 by 2 then 1 comma k squared tau. So that's one expression, but we can further simplify this. So what is hypergeometric function? If you look at the hypergeometric function for alpha, beta, semicolon, gamma, semicolon, some constant k, it's k squared, it's precisely this is the expansion. You start with alpha, alpha plus 1, etc. up to n terms. Then you do with beta, but alpha and beta are the same here, so you get the square. And in the denominator you have 1 plus 2, 3, etc. up to n, that's n factorial. And we had the n factorial, and then another n factorial because that's part of the hypergeometric function. So we took care of alpha, beta, and this one, and k squared to the power 2n is the definition, and this is a constant outside. So this is one expression.